Hello everyone, welcome to this talk on Fluidics integrated silicon photonics based continuous monitoring of electrolyte concentration in a flow channel. It's a mouthful for a title, but it captures all the essential elements that we would like to put together and also what we would like to demonstrate. So I'm Shankar Kumar Selvaraja, a PI in the Photonics Research Laboratory at Center for Nanoscience and Engineering at the Indian Institute of Science, Bangalore. The work is primarily performed by project assistants in my lab, Sandeep and Akshay. So here we are primarily going to exploit guided wave system for sensing. So when I say guided wave system, we use waveguides. So waveguide has this core where all the light is confined, and the light that is confined will have its evanescent field extending beyond the core that we have. So the extended tail part is what we call evanescent field. So this field is going to interact with the environment. And this evanescent field interaction is what we are going to exploit. So the surrounding environment will have its own optical constant or optical properties. And this optical property could change because of the density, concentration, or it could be temperature. So this can change the refractive index. And there are two things that can happen when you look at refractive index. One is the real part of the refractive index and the imaginary part, or the K extinction coefficient here. So put together, they are going to influence or change the refractive index. So if there is any concentration change or temperature change, then you will directly have primarily a phase change or just the real part change. You don't have any optical absorption there, provided the temperature changes are in a small range. But on the other hand, when you have K change, the absorption change here, because of concentration, you will see an intensity change as the light propagates through the system. So this is what one could exploit from the optical constant change of the environment by probing the interaction of the propagating optical field with the environment. There are multiple platforms one can use. A simplest form is a resonator that we see here. So this is a waveguide where light is getting propagated here, and there is a loop waveguide, and this loop is called the ring loop. And you couple the light inside this ring using, again, evanescent coupling. So there are certain wavelengths that will couple into the system, and they can stay inside this cavity longer than the other. And that is dictated by this phase matching condition, where the resonant wavelength, that is lambda here, is dictated by the geometrical path length, that is 2 pi r, which is the geometric path length, and the effective refractive index that includes the refractive index of the core, the substrate, and the medium. And put together, you form an optical path length, right? So if you look at this standalone response, right, without any change, that's a reference measurement, let's say, you get these nice dips corresponding to the phase matching that we see here. When there is a change in the environment, so I'm going to change the environment here. When the environment changes, the effective index changes. Because of this effective index change, the spectral response also changes. And the difference in this change is what we are trying to measure. And based on that measurement, you can back calculate the density change that we have. So this is exactly what we are trying to do. And in the past, we have demonstrated, very simple measurement using, drop casting of a fluid on top of this photonic device that will show us the spectral shift that we saw earlier. But then this is not so practical. This is good as a lab demonstrator, but then this is not practical for applications where you need, study of reaction dynamics, or you want to have some titration done, right? So you're unable to do that if it is just drop casted. And the other problem that you have drop casting is continuous vaporization. The concentration inside this drop casted volume, increases over time, which is something that is artificial. So in order to avoid all those, you want to have a fluidic channel. So what you see at the bottom right is this is a simple design where you have two inlets and you have a single outlet where the photonic devices are arranged along the flow channel. So that's on the right side, we see the blown up of that. So why do we want to do this? This is primarily to understand, the concentration of some of these electrolytes. Like, so in this particular presentation, I would like to go over how we make these photonic devices. How do we integrate this in a flow channel, and also demonstrate the potassium chloride and potassium bicarbonate concentration variation along this flow channel. And finally, would like to show a very simple titration between potassium bicarbonate and peroxide. And you might be wondering why potassium chloride and potassium bicarbonate and peroxide in this. So this has interesting application in energy. So primarily for water splitting and hydrogen generation using these electrolytes. But it's all done in volume, but the reaction kinetics are still need to be explored there. There are various methods people are employing, but in order to do a real-time monitoring, there is not very much scope in the existing modalities. So this integrated photonic monitoring system could be a potential substitute there. So this is how we fabricate our photonic device. So we start with a silicon on insulator wafer. So we have a silicon layer of 220 nanometer. And then we have silicon dioxide of 2 micrometer. So we clean the wafer and deposit or spin coat negative photoresist, electron beam resist, and we go through electron beam lithography process to define the waveguides. These are all shallow etched waveguides where the etch depth is about 70 nanometers. And then we clean and remove the resist, and then we deposit oxide on top, about a micron of oxide on top. So the reason for this oxide is to protect the parts in the circuit that need not be exposed to the analyte there. So we coat silicon dioxide and then followed by optical lithography process to open the windows. So these are all the exposure windows for our sensing activity. So on the right side, we see the optical microscope image of a sensing device where we opened up the region for exposure. So the next thing is to make these fluidic channels. So we use PDMS channels to transport fluids. So in order to make the fluidic channels, we use SU8 as a template. So we start by coating about 50 micron, in this case 100 micron of SU8, and then you do optical lithography. And then we use optical lithography to pattern these structures. So you have a rectangular channels of 50 by 100 micron. So they are 50 micron in height. Sorry, that the thickness is 50 micron, not 100 micron, and they are 100 micron wide. One can make it even smaller. So this is just the alignment accuracy that one can place these molds, but this is reasonably large for this application. So after making this SU8 template, we pour PDMS on top and cure it. And following the curing process, we release the PDMS. So after releasing, we place it on top of the already fabricated photonic chip. So what you see here is on the right side is such a template where we make this SU8, template on, and then when you pour PDMS, this is how it looks, and then we can release the PDMS. So what you see here, this is all fluidic channels in PDMS. It's transparent. And then after you make these channels, we can cut out this channels and then put it on top of the fabricated photonic IC, and then you can attach these fluidic inlets and outlets and then seal it with epoxy. So once you have this done, then you want to test the bonding strength. So we use oxygen plasma to bond these surfaces together. And then we do a leak test. So the leak test tells us, whether there is good bonding between the channel, the PDMS, and the chip, and we don't have any leakage. And this is the confirmation for that. And once it is confirmed, we do the measurement. So the measurement is done with such a probing stage. You have fiber in, fiber out, and then you have the fluidics. So the next step is to characterize the spectral response of the fabricated devices with the flow channel. So here, this is a simple spectral measurement that we did on the Mach-Zehnder interferometers, where we increased the concentration and we did see a redshift, which means the concentration of the environment is increasing. So based on this preliminary measurement, we went ahead and started doing various concentration flow through the channel. So we changed the concentration, as you can see here, from baseline DI water to about 2 molar potassium bicarbonate. So there are 3 spectral responses that you can see here. So this is just a response from the device. So again, this is an advantage when you use such a resonant device, where you can look at 3 different responses at the same time. And we pulsed between different concentration and DI water flushing. And on the right side, you can see an excellent match between the measurements that we do and the calculated refractive index change from on-chip measurements. So this is a very nice fit that we were able to get. And we continued the measurement with the potassium chloride. Here again, we see an excellent match where we can see that, this is the delta change that you can see for 3 different resonances. They are within the measurement error range. So on the right side, again, we compare it with the Abbe refractometer, which is a standard refractive index measurement tool. We were able to measure that as well with very good agreement. Following that, we did a titration measurement between potassium carbonate and peroxide here. So when you increase the peroxide concentration going through, or rather peroxide flow ratio in the flow, you can see decrease in the refractive index. So what this tells us is peroxide is actually oxidizing the bicarbonate, reducing the refractive index. And we were able to bring it back to the refractive index of the original bicarbonate when you reduce the flow to 0. Right. So this is a continuous flow, and we were able to measure these titrations. And based on this, one can study various reaction kinetics in this flow channel at reasonably quick time response as well. So you can see this is all happening within minutes, or if you closely look at it, within a few microseconds, these reactions starts to happen. So overall, through this demonstration, we have shown that the integrating this fluidic channel will be a versatile platform for various density sensing with various chemical components one can use. So we also showed an excellent agreement with the traditional Abbe refractometer. And the whole idea of doing this is to study these small reaction kinetics that one is interested in with different chemical composition. But at the end of the day, in addition to the density, we also would like to see what is the chemical change or chemical nature of these reactions by integrating some sort of spectroscopy on chip. Thank you very much for listening.